Okay, so if you bring your own laptop, please scan the barcode here. And I think today I want to mention about there are three kinds of programs, and they have two example data. So if you bring your own laptop, please scan barcode, or you can use the memory sticker here. Anybody needs memory stick? No? OK， 好 ，OK， 就是说今天呢，我的课程呢会包含讲这三个软体哈，以及这个还有这个我的 example 的这个范例的这个档案哈。那当然在做这个 structure refinement 之前呢，我会有一些基本的怎么去 collect 这个 data 呢哈，是我需要跟大家去讲的哈。So before we starting to refine our own data, there are several things we need to mention about is how to do this kind of experiment. If you do not do the experiment correctly, you would not get a good refinement. Okay? 好。Okay, so I will ignore the history of the crystal diffractions. But I want to give you a basic concept of the crystal diffraction. And then I will show you how to do the diffraction experiment, and then we talk about the analysis software. Okay, I will ignore that. Okay, so the basic concept of the powder diffraction is this is a typical diffraction patterns. So we will see shown here in the x-axis is the 2 theta, and the intensity is in the y-axis. So there very important feature is the peak intensity is proportional to the structure factor square, and the peak position is determined by Braggs law. And actually, the half width is also tell you about the particle size. So these three important features for the powder diffractions that we need to very careful when you collect the diffraction data. So shown here is the equation that I don't want to spend a lot of time to explain that, but you can get those knowledge from the textbook. So before the structure refinement and analysis of powder data, you need to have some basic knowledge. One is what is called a crystal plane and a Miller index. And then for those planes, they have a multiplicity factor we need to take care. And most important thing is what is correlated with the peak intensity. That is called the structure factor. And then there is a factor that will let you have a weak peak intensity and high angle we call the thermal factor. And of course, you need to know where the peak appears. So you need to understand what is called a Braggs law. And okay, there's two things. Another two things correlate to the equation and the below. So if you want to analyze the diffraction data, you must know that what is called a Miller index. Miller index is the normal direction about the crystal planes. So for example, this is the crystal axis along the A, B, and the C. So if we form a plane like this, 2, so we will call this plane is called the 0, 1, 0 planes. And for this case, this is 1, 1, 1 planes. So if you want to analyze your powder diffraction data, you need to know what is the basic idea of the Miller index. Okay. So shown here is the basic ideas how to calculate the 2 theta from the Miller index. So we started from the Braggs law. And if you have the Miller index, you just insert into the equation about the plane distance. And if you also know the lattice constant here, you will get and the X-ray wavelengths, then you can calculate the sin theta from those parameters. So this is an example. We got the 111 peak from the gold, and the estimated theta is 19.1, and the 2 theta will be go to 38.2. Okay, this is a very basic example. And the structure factor is tell you the diffraction intensity. So we can construct the structure factor from the unit cell. So this is an example. This is a BCC crystal structure. So we have two base point at the 0, and the half. So in this case, we did not use the duplicate precisions such like 001, maybe here, and 00010 or 011, because this precision is duplicate. So we only count these two items, and we insert to the equation here. So I don't want to spend too much time here. So you can get the structure factor from this equation. So it will tell you which kind of diffraction peak or middle index will appear in the diffraction pattern. So that's the most important thing that many students are not familiar in this case. What is called space group and the notation of the space group. So typically we always write the space group with the notation like the APQR, where the A is the type of your crystal, and something like it's a primitive or base center or body center, face center, or rhombic cell. And the PQR is the symmetry operators. So these two simple combine together and tell you the space group. But the detail, please go to learning the solid state physics. Okay, ignore this one. And here tell you that which kind of the space group will give you a corresponding diffraction peak. Okay, so here is the case that the structure factor will give you different load peak. So for example, for FCC, there's a 111.200. There is no 001 peak or 011 peak. There's only all even or odd peak in FCC phase. In the BCC case, there's the peaks, and HCP and they have their own rule. And the multiplicity factor is correlated with the duplicated plane distance. For example, we have the same distance from origin to the 010 or origin to the 0-10. So they have the same distance. So in this case, we have the duplicated factor about 2, which means they are symmetry and they also have equal d-spacing. And so does the 011 and the 111. They have different duplicate factors. So for the 010, they have a factor, multiplicity factor of 2. But for the 011, they have this factor about 4. But for the 111, they have the factor of is about 8. So typically for the cubic structure, we can say the multiplicity factor is proportional to the 2 to the n. N is the number of non-zero HKL index. But for the tetragonal or orthorhombic phase, they may not follow this equation. So what the influence of this multiplicity factor? So typically we can tell you the FCC have this, for example, there are 5 diffraction peaks. But if you consider about the multiplicity factors, they will times 8, 2, 4, 8, 8. So the final intensity will be look like this. So this is the reason why we got these factors results the different intensity. So this is for the BCC case, and this is for HCD case. Okay, so the other very important factor is called the Bywater factor. This factor is originated from the thermal vibration of the atoms. Typically, the atoms will locate at a certain point, but the thermal vibration will let the atoms move apart from the origin. So you can imagine that if the X-ray or neutron shine to these atoms, they will sometimes missing, right? Or they would be hit by at some certain point that of its origin. So they give you a form. They will have a equal cross section like this one. Okay, this is the original size of the atoms, but this is the effective cross section. But even this effective cross section is not 100% effective. For example, the atom moves here have a very low probability here, so maybe they have, at this point, they only have 10% probability hit by the X-ray or neutron. So it would be look like a normal distribution. So after some mathematical treatment, we will get this vibration correct from the typical structure factor like this. So you will see there is a thermal factor, or we call the Bywater factor, is in the notation U, which is the displacement from the center position. And its unit is usually in the angstrom square, which means the area, right? Because it's a cross section, okay? So maybe someone can use this diffraction, the Bywater factor, to calculate one parameter called the X-ray Debye temperature. That's totally different to the Debye temperature got from the specific heat measurement. But it is also an index that tells you how the atom's vibration in apart to its origin. So the final effect about the Bywater factor or thermal factor will let your intensity from this one to this one. So what does that mean? That means your intensity will reduce at a high angle. So this effect is also when you set up the experiments, if you spread your powder sample or your bulk sample that's larger than the beam start, it will also give you the intensity decrease with the scanning angle. So that would be very important. And this is a key issue that if you want to get the correct Bywater factor or thermal factor, you need to put your sample in correct position and the size. Okay, this is blood load. I think everybody already know that. And this is the way how to calculate the 2 theta position from the HKL. And for the practical crystal diffractions, for single crystal, you will get the diffraction points. And for the powder diffraction, you will get the diffraction ring. And if your sample is not well, like the powder, it will give you some spot with the ring. So typically, you can find this phenomenon from the TM image. So be careful if you do want to do the powder diffraction experiments. Make sure that your powder is fine enough. Okay. So this is the case. Okay. This is the powder diffraction rate. I got this data from the synchrotron radiation center. So that will give you a diffraction peak like this one. Okay. Just that. Okay, so here is the effect that I just talked about. If you put a sample like this way, sometimes for the in-house Xray, we have the configuration like this. So we have the two theta here, and we shine Xray to the sample stage, and we move this 2 theta from here to here. Okay, so if you put a sample, you spread the sample like this one, that's the typical way I found many students will do like this. And when the X-ray angle goes too high, you will find the X-ray beam will shrink to much narrow. So sometimes it will narrow than the width of the sample. So what does that mean? That means you use the different quantity of the sample to do the diffraction experiment. So in this case, the intensity will decrease at a high angle. But this phenomenon is not coming from the thermal factor. It's coming from you reduce the sample quantity. So that you must be very careful about this thing. Okay, so I just give you an idea about this effect. If you put the sample like this one or like this one, the angle dependence, this is the angle, okay, this is the normalized cross sections. The angle dependency would be look like this one. So this situation is even serious in the low angle. So you will find the intensity from 100% and decrease and reduce to the probably 25 or 10%, something like that. So you must be very careful for this kind of experience. Okay. So if you do if you set your sample not correctly, this effect will reflect to the thermal vibration factor, and it will give you the negative value when you do the structural refinement. So that would be a very important issue. Okay, so typically the solution we will narrow down the sample size. So sometimes if you go to the synchrotron radiation center and do the diffraction experiment, you will use the capillary. Capillary is very good container for powder sample because the configuration will be look like this. At any kind of angle, of course, in the synchrotron radiation center, the X-ray beam will not move. But this is just an idea that no matter at any angle, the cross section is always same. Okay, you will not change the sample quantity for the X-ray beam. Okay. Okay. The other thing is about the zero positions, which means that the sample would not at the center of the optical axis. So in this case, there is a parameter in the refinement called zero, which will tell you the sample just offset to the origin of the optical axis. Okay, here is the equation, so you don't need to remember that. Okay, but there one important thing is about the signal noise ratio. How to get enough signal noise ratio for the structural refinement? Okay, this is the way how to calculate that. In this diffraction patterns, this height we call the signal. So in this case, the count would be 43, and this fluctuation, the amplitude of this fluctuation is about 16. So we call this is noise. So if we want to reduce the signal to noise ratio by 2, then we need to times the time by 4. So if we use the, for example, if we collect this pattern for 10 minutes, then we will get this kind of signal noise ratio. We need 40 minutes. Okay. So this is the way how to calculate the signal noise ratio. Sometimes, I saw many students want to increase the signal noise ratio. They just increase the points. But that's not the case. Because we need to reduce the signal noise, we need to integrate the certain point by longer time. So if we keep the same step, but we increase the time by 4, then we will reduce the signal noise by 2. Okay, you got the point? So this case, it may be correct in 10 minutes, and this is for 40 minutes. So we got the better signal noise ratio by 2. Okay? Okay, another very important issue is how many points you need to collect in single peak. So for the structural refinements, we know there are profiles. So we typically use the Gaussian profile and the Laurentian profile. Sometimes we combine these two profiles, we call the pseudo-Voigt profile. So here are many parameters. Here the P0, mu is the ratio between the Gaussian and the Laurentian, and the A. This A should here should be another A here. Okay. So we need to how many parameters we need to have is P0, A, mu, and the theta 0, and the width of the Gaussian and width of the Laurentian. So there are 7 parameters, and for the 7 parameters, we need to at least 7 points, right? That's a simple mathematic rule. But if you want to have a statistic meaning, you need at least double the parameters. But we need the odd number, so at least if you want to solve one peak, you need 15 points for each peak. Okay, this is the basic idea. Okay, so these are the some issues you will meet when you use the powder diffractions. And now I want to introduce the software to how to solve the crystal diffraction pattern. Okay, the typical one we call the Jesus2, but today I want to introduce another one first called the Expo 2014. That would be very, very easier for the elementary user. Okay, but the Jesus2 is more professional, and you will find that the software from many papers. And Jesus2 is a unique and comprehensive open source Python project of determining the crystal structure and the diffraction-based material characterization for the crystalline side on all scales. Okay. And the other software is called the Vesta. Vesta is developed by the Japanese guys, and it is good to plot, to make a draw about the crystal structure that from your refinement. So both software is very important for the structural refinement. So you can download from the following link or just from the barcode I present in the beginning. Okay. So here is the feature. This is the Vesta, and this is the Jesus2 with its set up window. We can plot the diffraction pattern with your refinement. We can also plot the crystal structure with the electron density. So depending on what kind of information you need. Okay, so typical process you do the refinement is we can start from the original crystal models. Typically, we will use the CIF file, CI file, which means the crystal information file. So those CIF file you can download from a crystal open database. So I will show you the link later. So if you have the CIF file, you can refine the background and the scale factor from your diffraction pattern. And if you got the best solution, you can stop the refinement. But typically, you would not finish that at the first time. So you need to refine lattice constant, 0 point position. So here you can also see I just highlight in the equations which parameter that you refine. And if you got a better solution, then you can finalize your refinement. If not, you need to refine the peak profile and the atom positions and the temperature factor. And then you can loop follow this process. So typically you will see that if you just refine the background and the scale factor, you will find, okay, the black line is the extreme data and the red line is the you want the refinement result. So if first refine the background and scale factor, then you will get the match like this. And then you can refine the lattice function and 0 point that will shift your 2C position. So you will look much better. And if you refine the profile, then you will get the shape like this. And if you also refine the atom positions and the thermal factor, you will look like this one. So I think that would be the final stage if you refine everything. So there's 3 factors very important in the refinement. The first one we call the reliable factor, which is the point between the experiment and the calculated data. So RP means the observed subtracted calculate, okay, divided by observed. And the RWP means we weighted at the pressure near the peaks. So this is a weighted reliable factor. And the chi-square is look like this. So typically we need chi-square less than 2 and RP less than 6% and others less than 9%. Okay, so those are the basic technology of the structural refinement. So here I want to do a demonstration for you, but we will first study another software we call Xray 2014. Okay, this is the software developed by Italian group. So before that, I need to introduce the data format. So typically when you do the Xray experiments, you will get the data format like this one. Okay, maybe we could go to this one, okay? So the data format will look like this. This is the 2 theta and this is the intensity. So we call it raw data, okay? So how to and you also need have the zip file. Zip file I just say is crystal information file. It also the pure text format. It will look like this. And you can download it from the Crystal Open Database. Okay. So let me just give you a demonstration. Refine that with the export. This is the program called Xray 2014. If you download that from the website, or I just give you the barcode, and if you still need that, here is a memory stick. You can borrow from me now. Okay, so how to refine the Xray diffraction pattern or neutron diffraction pattern for export program. So first thing is you open the file and import diffraction pattern. For example, I go to this one, and this is the raw data I just showed you is C2O XY, and open it. And you can select which kind of the light source you use, the X-ray, synchrotron, neutron, and you can also adjust the wavelengths. For example, this diffraction pattern is correct from the commercial in-house X-ray machine. So I will use the typical X-ray with the lambda 2. And then I can import the structure from the zip file. So here would be a sorry. Okay, that should be because here. Okay, just missing here is the crystal structure just outside the window. Okay, because of the resolution issue. Okay, just forget about that. The only one thing you need to do in this software is just click refine and click retrieval. Retrieval is the method how we have to mention about how to refine the powder diffraction patterns. So you just click automatic refine profile and automatic refine structure and click refine. Okay, everything is done. We just define the patterns and all the parameters shown here. So you will get the latest parameters and all the profile parameters here and the R factor here and chi-square. So everything just one click. Okay, so I think that for the most user, you just need this program. We don't need to have knowledge about the crystallography because typically you just need the latest concept, right? But everything just refine here. Okay, let me show you another example with this software. So here is another more complicated structure. First, import the diffraction pattern. This is the diffraction pattern. Is the Xray, and we also import the structure. This is a zip file. Okay, let's do it. Go. Okay, done. Finished. So it's quite simple, right? So all parameters you can check here, information file, view output file. Go to the button. So this is the, oops. So okay, these are the atom positions and the latest constant here. And if you want to show your refined parameters, okay, here's the R factor. So everything just done in 1 second. Actually, not 1 second. Okay.
Why the refinement result shows a negative divide 1 factor?
Oh, okay. Because this sample do not set up correctly.
Oh, okay.
It's not the, if it, most time if you use the single strand Xray, because they use the capillary, so you will not get the negative thermal factor. In this case, it's not the commercial Xray, so we just spread the sample with the very wide size, so you will get the negative thermal factor. Okay. Any other questions for this software? Well, you can also export your own zip file. So let me check. Can I move the Windows in? Wait a moment. Okay. So this is the actual refined structures. So you can export the zip file. You can export the structure somewhere, which is also the name of the zip file. Okay, that's your own refinement. So you can use this. We use this zip file to different sample. Okay. Any more questions? But there's a very very big issue in this software, which is it can only refine for the single phase. If you have a multiple phase or you have impurity, it will not work in this software. Okay?
Sorry, another question. Can this software also perform sequential refinement?
Sequential refinement?
Yeah, like if I got
Sequential,
yeah,
right?
sequential.
No, no.
Okay.
It's just for very simple diffraction pattern. Okay. Okay, so we will go to Jesus2, and for the Jesus2 is more complicated, but you know complicated means that it's a multiple function. So you can solve the complicated patterns. For example, maybe they have a dual phase in the sample, or there's some, if you want to solve some impurity from your diffraction pattern, you can use the Jesus2, and you can also plug the electron density map in this program, and there are another plug-in you can do different things. It also can do the sequential fitting. But I think today I did not prepare for that. But you can find the how to do the sequential fitting from the website. I don't remember did I make a record about that, but you can find it from the YouTube. Okay, so I just give you a very brief demonstration about the Jesus2. So we start from the simple one. So if you just install the Jesus software from the barcode I just give you, or you already have one, then you can start with this batch file. Okay, this is the main setup window for Jesus2. And in this software, you need to import the diffraction pattern. From here, there's the import and the powder data. And typically, you don't need to know what kind of the data format you have. There's just one thing you can let it to guess the format from file. So for example, I go to the simple one, which is CO2O, it's a cubic base, and I just import the diffraction pattern here. And then one more thing for the Jesus2, you need to give the instrument file, which means that this file contains the instrument resolution and the 2-theta range, but that's the matter because you need this initial file, but you can modify at any time. But for this software, you must give the initial file for this software. So here is the instrument file. Okay, I forgot. I can show you the data format of this. So this is the data format, and this one tell you this is the powder Xray diffraction, and its wavelength is there are two wavelengths. One is K alpha 1 and this is K alpha 2, and this is the ratio for the K alpha 1 and K alpha 2, and this is the profile for the Gaussian and the Lorentzian, and there are some asymmetric profile. You don't need to remember that. You can get this. Typically, when you go to NSRC, they will give you this instrument file. Okay, don't worry about that. If you do this experiment in your own in-house machine, maybe you can find this file from the internet. You can just search about the INST, Xray, and INS. Okay. Okay, so this is the window that we just import the diffraction pattern, and this is the setup window. Okay. And typically, if we just import the diffraction pattern, we can also import the CI file. So here is the way we can just import phase, and in phase you can import the previous refinement result, which is the format called the Jesus2 GPS file. You can also import the zip file here, and you can also import all the Jesus1 ESP file. But for me, I always use the guest format from file, so it will guess the file format automatically. So I can use this one and import the zip file. So it will ask you if you want to read this file. So I will select yes. And here is the face name. You can type by your own, or you can just remove that. For me, I can write this BCU20. Sorry. CU20 in cubic face. Okay. And okay, sometimes if you import a zip file, they have two different origins, because in the same space group, sometimes they have different notations. So the origin will shift sometimes from the 0, 0, 0 to the half, half, half. And in this case, it recommends you to shift the origin to setup 2. So you can select the shifted origin 2 or keep the current coordinate. Okay. For me, I will first try to keep the current coordinates. And then you need to link this zip file to the patterns. So this is the very important part. If you have a multiple diffraction pattern, you can just there will be a list for the multiple patterns, and you can click which the diffraction pattern you want to link to with this refinement. Okay, but in this case we only have one diffraction pattern, so we just click one. Okay, so if you just import the correct zip file, you will find there is a face, and there's one more window you can set up here. But before that, we need to first to give the background to this diffraction pattern. So I will go to okay. Let me do more explanation for this. So there are two parts. This part is for the sample and the instrument setup. So there will some parameter called background, instrument parameter, and the sample parameter. And for the phases is the theoretical parameters that you guessed the crystal structure. So this is for the practical experiment. This is for the theoretical guesses. So in the beginning, we need to set up a parameter here to tell the programs what kind of setup you already used. For example, we need to tell the program where is the background, and there are some instrument parameters. For example, if you change the slit size, you will get if you narrow down the slit size, you will get the narrow peak profile. So you can set up here. And sometimes you also need to set up the sample parameters. For example, there would be some quantity and absorption coefficient, something like that. So we will set up from the background. So typically the background would not flat. So we will change the number of the coefficients, because we can fit that with the polynomial. So typically we will set up this parameter from the 12 to the 18, depending on the how complex of your background. Okay, and we can, but there's a many parameter. Where is the background? You can tell the programs. So we can add the background here. So there's a fixed point. You can click the add, and we will go to the this pattern. First, we adjust enlarge here. Okay. Open here. Open here. And here the background, here the program background is over here. Okay, we will erase the this additional this point in the data. So here are the background. And I want to remove this one, and this one, and this one. Okay. So we'll go back and we will fit the background. Okay, that looks good. So we have a background now. And then we'll go to the instrument parameter. Then I can refine the zero offset and the profiles. So in the beginning, I don't want to refine anything. So just leave blank here. And here are the sample parameter for the histogram scale factor, which is associated with the quantity of your sample. So you have more sample, and this factor will become larger. And I just leave the check here. Okay, so I think that everything is done. I can start in the refinement. So we can do calculate and refine here. But for the first time, the program will ask you to name this project. So we click the refine. Then here we need to input the name of this project. Okay, they will tell you the refined result. So here's the chi-square is like this, and it will ask you if you want to load the new result. Sometimes if your refinement is over the limit, you will need to cancel the refine. But in this case, we can load a new result. So I just click OK. So this is the initial refine here. So you see the green curve is the calculated value, and the blue one is the experiment data, and this color means the difference between the experiment and the calculated value. So it looks like the peak position is correct, but the width is not good enough. So for me, I will go to first go to the instrument parameter, and then the zero be refined. And here are UVW and XYZ. The UVW is the parameter of the Gaussian, and the XYZ the parameter for the Laurentian. So typically, I will go from the higher order of the parameter, and I will use the hotkey called Control R. Okay, so the string comes better, and I will open the lowest order of the parameter and run again. Okay, looks good. And finally, I will open all the parameters. Control R. And now you see the refinement looks good, but you still not refine the latest parameter and the atom position. So I will set the flag for the coordinates, and we'll go first. Okay, so in this window, it will tell you there are some problem for these two parameters, which is U and the V. What does that mean? That means they are highly correlated parameter. That means if you increase the U, then V will also increase as well. So they are highly correlated. That's the meaning. So in this case, I will close the U and V in the refinement parameter. Let's go back into I will close. Actually, I will close all of them. And I will also open the refinement for the coordinated thermal parameter, and I will Control R. Okay, so looks there's no problems, and the refine is good enough. And maybe you are curious about in Jesus, can you plot the crystal structure? I will tell you yes. So there's a window I can set up here. So we can clinically draw atoms. So this is the initial window for this crystal, but typically you need to fill all the unit cell, right? So what's the problem? Because the Jesus do not fill the atoms in one unit cell. So you need to do is to edit the fit and fill unit cell. And I will select all the atoms to fill unit cell and click OK. So you will find the atoms are fully filled in one unit cell. Okay. Any question?
如果要是非多笔数据的话，
我今天没有准备这个，可以的。就是刚刚在这个输入的地方，对不对？你就把它全部都弄起来。但是有一个 key point， 就是有个地方要选那个 check， 就是说你要 fit 5笔数据，它其实5笔数据有2种情况，一种是它5笔数据是彼此有相关的，比如同一个 sample 做变温，那就要去 check 那个数据，有个地方要打勾，但是我今天没有准备，没办法去秀那个部分。另外一个是5笔数据，只是说我5个不同的样品，但是都是大概同一个结构，那就不用去劝它，就是勾，它只会 fit 的。但是在一开始的时候就要输入那5笔数据，其实是可以的。对，那有一个 key point 啊，就是同一个样品那个地方，因为我今天只有2个小时，所以没办法去讲这么深入的东西。是啊，等一下我会再讲一下电子密度，还有一点点时间吗？差不多嘛，可以讲。还有谁？Any more questions？
那diffraction factor 的影响在哪？
啊，diffraction factor 的影响哈，我直接手动调数字给你们看，你们就知道 diffraction factor 实际上影响是什么哈。I will do the manually adjust the diffraction factor, and you will see the influence on the diffraction pattern. 好，来，我们来看一下哈。如果在 atom 这个地方，你看这里的 U 哈。好，大家看这里 UISO 哈，这是0.002、0.004哈。我现在假设把它改成怎么样？我全部把它改成，等一下我先把其他参数都关掉哈，免得影响这个测试哈。好，你看哦，我把这先把这 XU 关掉。好，假设我把这边全部改成，比如说我举个例。我改成0.8。那请大家看一下我们的 diffraction pattern 变成什么样子的哈。有没有看到？它这个哈，当我把 U 改得很大的时候，你看到哈，我这个比较 fit， 这个就不 fit 的，然后会其实越差越多。就是我刚刚讲的哈，在高角度的时候呢，你的 U 不对的话，会越差越多。所以它会在高角度的时候特别表现出你的差值。这是一个，那如果说你铺粉，刚刚我讲铺粉比较高角度的时候，你打到的粉比较少的时候，对不对？你强度本来就会比较低嘛。可是呢，程式当然不知道，是因为你铺粉铺的比较宽，导致你的这个样品被 X 光照射量比较少，结果他就把所有的过错推给 thermal factor， 然后你就会得到负的值了，这样子。
OK， 今天还有1个小时。
啊？
是2个小时。
对，我本来预期是大家会带 notebook 来，我可以带大家做了，然后所以我就没有准备很多。没有，先画电子密度的。So I will show you how to plot the Fourier transform electron density map. For the Xray, we will get the electron density map. For the neutron, actually we will get the diffraction density from nuclear. Okay, so that's a different meaning. So how to plot the? Okay, wait a minute. I need to restore the. So how to set up the just this one. Okay, how to plot the electron density from the diffraction patterns. So first things we need to set up the Fourier map from this window. Okay, so we go to the journal, and there is a, you see here, here's the Fourier map control. So we can set the map type. So there are different types. So first one is the FOBS. What does FOBS mean? This means Fourier map for observed. Okay, and then this is a Fourier map for calculate. So from first one, if there will be some noise spot because you just calculate from the real experiments. And for this one, you have got a very clean map because there's all come from the theoretical value. And there is delta F. What does delta F mean? That means the Fourier transform from the difference between experiment and calculate. So sometimes you want to find out the missing atoms, you can use this map. Okay, because there's some intensity you did not calculate from your structure, right? But in the Fourier map, you will find out there will be one spot. Maybe, for example, if you have some very light elements, it would be not taken into account in your diffraction pattern. So you can find out the location from here. So the delta F is most useful for some new compound or some missing atoms. Okay, and for the others, I have a different specific usage. I don't want to talk about too much about this. But now I want to set up the Fourier map for the observed. So I will choose the FOBS here, and then I will select the reflection set. So this is the diffraction pattern that we just input. Okay, and I think that's all. So we need to first calculate the diffraction refinement, and then I also need to calculate the compute the Fourier map here. So here is the compute, and this is the Fourier map. Okay, and then we can export the map as Fox or draw crystal file. So for example, I just export the grid file here because we already calculated the Fourier map, so I can export. And when I export the result here, then I can go to okay. And here we will use the second program called the Vesta. Okay, Vesta, I just talked about it, developed by the TWNSS group. And if you download that from the barcode in the beginning, then you can open this file with by Vesta. So I can double click this one, and I can go to Vesta. Okay, you can see that this is the Fourier density map in 3D mode, and we can set up this one. Okay, loading. Different resolution here, and I can do the for example, I can first to set up the density map. So for example, I can surface, so I can rent it and change the isosurface level. For example, I just set it to 1. And you can see the density becomes a difference. And this is an example. I can plot the electron density map, or you can cut into slices. So we can use the 2D display. And so I can slice it along specific Miller index. For example, I can slice in HKL is 001 from X and Y limited from 0 to 1, 0 to 1, and 0 to 1. So this is the slicing Fourier density map. And you can also show the control here. with linear or logarithm mode, and you can set up the the spacing for each level, and maybe I can start in the different Miller index. For example, I can start in the HK is equal 111, so it would be look like this one, and I can also do it. Okay, this is the steps. Maybe you can modify to 10. And okay. Okay, I can also show the absolute value. And okay, I think that's the only function that you need. So sometimes we want to discuss the bonding, so we need an electron density map. And if you cut into slice it along the different crystal plane, you will find where is the connection between the atoms, okay, or the rod or bridge between the atoms. So you can use this function for your refinement. So any more questions?
If it is an anisotropic crystal, like 2D material, so how to judge, okay, the preferred orientation, the weight of
Preferred orientation, okay. That's a tough question. If you want to calculate the preferred orientation, in the Jesus2 there is only one preferred orientation, is a node. There's only one. But for the Jesus1, you can assign multiple preferred orientation, because sometimes if you make a single crystal, right, if you grain it not so fine, you will have multiple preferred orientation. So that makes sense in the Jesus1, you can set up many different preferred orientations. But in Jesus2, it will tell you perhaps you make a polycrystal back. So there only one preferred orientation is low.
So how to set it in
Now?
Jesus2? Yeah.
Oh, okay, I can set it. Okay, so if you want to set up the preferred orientations, that would be here. So you go to the data. There are many different properties you can set up here. For example, you can calculate the microstrand. Here, microstrand. You can also determine the particle size here. Okay, of course you need to subtract the instrument resolution, but it's done. For typically here, just assume the instrument resolution is infinitely narrow, right? So there's no instrument resolution issue, so you can just directly particle size here or domain size here. You can also calculate microstrand. And if you do some pressure experiments, you can set up some hydrostatic or elastic strain here. But if you want to set up preferred orientation, we will use this one. Typically, we will use the MD model. So the MD model means that the orientation along the how to say that? If you have a preferred orientation along the normal direction, then you can set up the HK or Hs here. For example, I can set up the I just click this one and use this model, and I can set up the preferred orientation like this one. Of course, I can manually to change these things. So perhaps if you want to increase the intensity along the 111, that means you have a preferred orientation along 111, right? You need that this value becomes smaller, less than 1. So you will get a stronger intensity along the 111 direction. Okay, I can do it for you. So if I set up this value to, for example, 0.5, and then I go to 5, you can see the okay, you see that? The other Miller index show the less intensity and only for this one we will get the solar intensity. But you need to set up this parameter below 1. Okay? Any more questions?
Yeah, so if I got a sample, it shows the charge density wave phase, then if I want to find the modulated electrons, if I want to locate those electrons in real space, can I use the delta F Fourier map to do that?
In principle, you can do that. Try this one. Yeah, yes, because we will see some missing intensity, diffraction intensity. So if you use the Fourier density map, perhaps you will see such kind of thing. For example, in my PhD thesis, I ever do one thing. I just find out there is a charge ordering, so we can find that from the diffraction patterns. There's not only extra peak, there's also have a very broad peak at the low angle. Typically, we will say that would be gas state, right?
Yeah,
but
yeah.
for that case, if we do some Fourier transform, we will find there's a link along the different at the different orientations. So I think that it would be possible to find the charge density wave.
Thank you.
But you need to do this very more carefully. But there is no problem for the NSRC. Yeah, actually, in my PhD, the charge my charge order is only found in the single zone radiation Xray, but not in in-house Xray. Okay. Any more questions? Okay, good question. We can also solve this unknown phase from the Jesus, but you will use the function here. Okay, wait a minute. So we first okay, just here. So there's a very old problem we call trio, but the trio is the problems to looking for the unknown structure, crystal structure. So if you just import the, I can do a new for you. So if we don't know this crystal structure of the Cu2O, okay, just close everything. Can start here. So first we also import the diffraction pattern here. This one. Okay. And instrument parameter. Okay. If we want to guess the structure, we can set up in this window. So we can guess the first thing is we can give the size of the size of a crystal. We can make a guess, right? Because you already know, at least you know what kind of compound you have. For example, you at least you know there's a 2 copper and 1 oxygen, right? So we can make a guess. For example, maybe the cell volume would be less than 100 angstrom cube, right? So you can put the start variant here. And because you have no idea about the phases, right? So for me, I will click almost everything except the monoparameter, because the monoparameter have too many parameters, so it is not able to find out in these programs. And then I will refine. Okay, but there's one more thing. If your crystal structure is a modulated phase, that would be more complicated. So in my opinion, I would not suggest you check this one and this one. So for me, I will only check all of this structure. But the one more thing, you need to tell him where is the peak positions. So you also need to set up the reflection list here. Okay, but wait a minute. We need to first find out where is the peaks. Okay. So we can do it automatically, but you know that's too much, right? But just forget about that. If we agree that those are peaks, right? Then we can go to the window here. Okay, you can uncheck the peak that you don't think they are real peak, and we can go to the this part and then it to do the cell index. Okay, you need to do at least one time to fit the peak, and that should be peak list. I need to reduce the peak number, okay? So first thing you need to search the peak and save the peak. Then you go to the window that I just set up, and then I can index the peak. And after you index the peak, it will tell you there are many space groups. And once you got a space group, you need to insert the atom individually. So for example, if you give you the space group like Fm minus 3m, then you need to fill in the atoms. For example, you need to put the copper at the position in this phase, say 0, 0, 0, or half, half, half. Then you need to make it. You need to try if this model is fit your diffraction pattern. So that would be do it manually. And in this mode, I think for the simple structure it would be easier. But if you want to looking for very complicated compound, that would be very, very difficult. So sometimes we will start from some isostructure and iso compound. There will be a structure will be very similar, and I will just do the things that I will insert atom at the same place in the different compound. Okay, or just make some replacement. So that will be much easier. But you really want to index a known sample or a known compound, that will be take times. For example, my PhD student just he identified one compound which contains 352 atoms in the crystal. He spent almost 1.5 years to solve one compound. Okay. But for CO2O, maybe you can do it in 1 day because there's only 2, maybe 3 positions in unit cell. Okay. Any more questions? Is that okay? Okay, start. Any more questions? We still have a half hours. I do not expect you to not bring your own laptop.
我觉得刚刚那个铺粉为什么造成 diffraction 那个，我觉得可以用中文的介绍，就是那个 铺粉铺的圆圆的，或者是铺的平平的，大跟小。我那边我觉得可以那么解释一下。
Okay, so Professor Wei asked me to explain how to spread your powder sample in the sample stage in Chinese. So I will explain that again for you. Okay. 好，我换中文来解释哦。这个部分呢，其实很多在做 refine 的时候呢，通常啊，其实即使是 X 光厂商的原厂他们给你的那个 in-house 的 Xray 的 holder， 它其实都是一个方形，然后挖一个洞，而且是一个长方形的洞，大概可能就像这样的一个长方，没有那么大啦就挖长方形的洞。那通常呢，因为大部分的使用者他只是要去对 JCPD 的资料库，所以强度不重要，那没有什么问题但是呢，假设你要做结构精算的时候，这就会有一个大问题我举个例你现在看低角度阳光斜洒下来的时候，它是会洒起来会一大片，对不对？洒起来那个截面积很大嘛，对不对？所以呢，假设你的样品布得很宽的时候，在低角度没有什么问题，所有样品都被 X 光打到了，所以你收到的讯号是由所有样品给你的讯号。可是你铺很宽的时候，当你 X 光到高角度的时候，像阳光直射的时候，你的影子就会缩短，对不对？它只打到了假设我铺了很宽，我只打一小部分的 sample， 所以什么意思？你是用不同的样品量去做实验。那不同样品量做实验代表什么意思？什么样比较小？比较小是 X 光到高角度，高角度的时候样品量比较少，那当然强度一定会低嘛，对不对？可是我刚刚又讲了一个因素假设没有这个样品量不同的因素的话，我到高角度的时候，因为热扰动也会让我强度降低。那你想想看那你今天去做结构精算的时候，假设你是因为样品铺得太宽，导致说在高角度的时候，真正被 X 光洒到的讯号比较少，造成的降低的话，程式是不懂这件事情，程式没办法去修正这件事情的，所以他把所有的过错都推成谁？都推成是因为热扰动造成的降低。所以去做refine的时候，很多时候你会得到负值。然后呢，其实这有一个误区啦，就是说以前一开始的时候，我的这个有部分学生在做的时候，同步辐射做起来都不会是负值，同步辐射果然是比较优秀。那其实你有做过同步辐射就知道，因为同步辐射用的是什么？毛细管 ，capillary 是毛细管，然后同步辐射病呢，都可以把那个毛细管那个 cross-section 要 cover 住。那虽然它也会转，这个同步辐射会转，那个毛细管会旋转，所以呢，第一个它打得均匀，第二个呢，它的这个截面积永远都是那个圆的半径，所以它没有样品量变多变少的问题。但是这个呢，有时候铺粉就会了，所以在做 refine 的时候呢，你铺得越宽，你会发现你高角度掉得越快，就会出现这个问题。那所以在早期以前，因为我老板是李文宪老师啦，他会拿一个东西是这个没有被光的这个对吧 sample hold 对吧样品座是不是然后放一张荧光纸 ，X 光照下去的时候，比如说我今天做角度要做20度到80度，会看到它 X 光最后缩小到多宽，我铺粉只会铺在这个宽度之内，我不会铺超过那个宽度。对不对？因为其实你不要管这个 refine 怎么样，你做实验的时候 ，X 光打到样品量不一样就是不对嘛，对不对？这几何很简单的几何问题嘛，你一定要让它样品量是一样多的大概的概念是这个样子然后呢，其实这边我可以用中文再讲一次有几个你要做 refine 前，你 Xray 要很注意的事情，就是第二个，你的这个。这是我刚刚讲的热扰动会造成你的强度在高角度降低。虽然下面我写的是塞西亚摆烂达，那基本上跟西塔有关然后这个 zero 就不用讲SNB 这个是一个很重要的一个概念因为有时候我会跟同学说，你的refine你解析度要够了但是同学会误会解析度这件事情解析度这件事情其实还有 SNB 这件事情呢这两件 事情很重要啊，就是说，我说你那个refine，你可能这个 SN 比要做清楚一点啦，结果同学把它点加倍就多了更多时间。然后呢，你想想看，你去做同步大概没有这个问题，同步大概就是几秒钟就搞定。如果你是 in house Xray 跟人家约的话，1小时变4个小时哈。说老师我做的更密了哈，就你这边变得更毛，因为你点变更多了。你不应该把时间用在增加点数，而是应该要增加它统计的时间。所以统计的时间，我刚刚讲哈，讯号是从这个 peak 的底部到这个大概的中间点顶部，这叫做讯号，这个叫讯号。这个毛毛的这个起伏的宽度叫做杂讯。杂讯对讯号的这个比值，以这个例子来说是16:43，对不对？假设你做了10分钟，是这样子的话，你要讯噪比把它变成8，就 SN 比少一半的话，你时间要乘以4哦，因为它是正比于那个平方结构因子的平方，所以你去做这个大概是 count per second 啊，你说，增加4倍，我强度变4倍啊，不是，你如果用每秒钟多少哦，就是你把 normalize 对时间 normalize 的话，你 SN 比就会提高了。所以呢，我刚刚讲了2个重点，第一个就是说，到底要取多少点叫做够，在refine上是够的，那我刚刚讲说，基本上我们比较好的话，希望一个 peak 有15个点啦，这是统计上的要求啦哈。那你多于15个点可不可以？当然可以啊，但是你时间要够啊哈。那只有同步这种可以奢侈的随便打哈，你可以统计久一点，对不对？一般 in house 的话哈，你这个通常一个 pattern 做起来就可能会做到1个小时啊，甚至10个小时啊，因为那现在 X 光管那个耗材很贵啊，对不对哈？那无形的成本，你现在把 X 光管烧得太久，对不对？坏掉了，老师最后你的学弟妹就要承担你的苦果嘛，对不对？同步没有关系啊，同步随便打10秒钟，打1分钟，好像还没有打超过5分钟啊，那 detect 会爆6553会爆掉啊，所以同步可以那个点同步点也没办法无穷点啊，就是说基本上这个不是在打同步没有问题，要打一般的 in-house Xray 的时候，如果你约的时间是有限的，那你就要去精算这 SN 比。那一般 SN 比要多少？我们在做精算的时候，我们希望至少啦1:10啦，好的 refine 1:10，不然的话你的 affect 会很难看，那所以其实要做 refine 前，你要把这些 SN 比你要做的点数这些功课全部做好，再来做这个 refine， 还有样品怎么铺要把它放好，没有被光了什么东西去弄好，再来做这件事情。那不然的话你随便打，因为我常常看很多的 X 光的 pattern 都很毛，那很毛的时候呢，有人会跟我说，老师我发现它有一个 cubic to tetragonal 的相变，只有2个 peak 哦，那这个连自己都说服不了，对不对？所以就必须要把这个事情做好啦。那
就是可以帮忙大家介绍一下，如果你有过筛跟没过筛的差别，然后你
好
在in-house
过筛跟没过筛你的那个粒径的均匀度、粒径的大小，其实跟你半高宽有关。那刚刚的我已经把它关掉哈。刚刚在refine的时候，它有一个那个粒径的那个粉体的 size 啊一般来说这当然跟 X 光的 slit 有关你 X 光的 slit 基本上小到一个程度的时候，你发现你任何一个 peak 的半高宽通常就不会再小了。我举一个结论，假设你做 silicon 的单晶，你去打，通常在61度的时候，有一个很尖的 peak。通常我会把那个东西当做你的仪器的解析度。通常我们习惯用这样子。好，那个东西呢因为单晶代表什么意思？单晶代表说我的周期性呢是无穷长的，对不对？那我们反过来一件事情，你把这个单晶把它切得很小，越小，小到比如说1 micron到1 micron 的时候呢，通常那根 peak 还是很尖的。当你小于1 micron 到 narrow size 的时候，你会发现半高宽越来越宽，越来越宽。为什么呢？因为你小于这个其实有公式可以算的啦。那今天这个没有办法去讲，就是说你小于一个 size 之后呢，它的这个颗粒的边缘效应就很重要了。因为边缘的话，你想想看，我干涉，什么叫干涉？我跟隔壁人可以干涉，对不对？那你隔壁人还有隔壁人，他也干涉，可是到最旁边那个人怎么办？就没办法干涉嘛，对不对？好，当你有1000个人，只有左边跟右边2个边缘的时候，2/1000这大概你看不出那个没有干涉的地方。但是如果只有10个人，但是你的边缘左右2边的话，那没有干涉的比例就很高了，20%，对不对？ 好，所以呢，那个颗粒的大小会影响你半高宽的峰值。好，那我其实这件事情呢，哈，刚刚魏教授问这个事情非常好，因为以前我专门做过这件事情。假设你的样品没有过筛的话，你有一个分布的话，你的去做refine的时候发生什么问题呢？当你大颗 pick 会很尖，尖的不得了，小颗 pick 会一包，结果它得出来的风型是一堆变成这样很尖，然后尾巴拖很长的两边的东西，好，那你就会得到一个分布，好，那一般refine的分布是假设你的粒径，看刚刚一开始它假设都是1 micron 均匀的1 micron 的颗粒去，所以你去做同步的时候，一般会要求嘛，对不对？要磨细一点，那个 powder ring 才会漂亮嘛，对不对？哦，那一般来说都是1 micron 嘛，哈、哦，研磨要研磨到 nano 好像要比较特殊的机器啦，哈，一般啦，哈，这当然不是绝对的。所以呢，假设你的粒径有大有小分布的话，哈，在 micron 之上可能问题不大，有一些 micron 或者有一些碎片在里面的时候，你就得到下面是这个很拖两边的，所以有时候你会发现有一样品会长这样子。那这样子的时候，你去refine的时候，你发现你 pick 怎么 refine 都不好，有的就是要么就是两边 fit 不好，要么就是上面 fit 不好，哦，怎么去 fit 都很难处理。所以有时候我们就会希望你这个样品去过筛，哦，当然过筛有个好处是，假设你要做毛细管，你塞得进去啦，没有过筛塞不进去，这样子，哦。那还有一种就是做 2D material 的时候会常遇到的是，它的风型是一个不对称的，它是一个低角度是以你们角度来看，它是走，比如说这个是背景，然后到某个 peak 的时候突然上去，然后呢尾巴拖很长，啊、尾巴拖很长。那这种呢，这个 GSS 就没有办法处理的啦，这个要另外写程式去做模拟的啦，因为它是一个 asymmetry 的一个风型，那原因是因为 2D material 它沿着某个晶面的这个层数很少，很少的时候我反射的时候不是无穷多的时候呢，我在不同的角度的时候，这个很薄的这个层的反射的这个次数呢是不一样多的，所以随着角度一直变化的时候呢，它的强度会慢慢降低，可是它不是一下就降到没有，所以会拖很长，就很难去做refine。这也是一个很常见，因为现在很多人做 2D material， 所以看到这样一个不对称的风型啊。是。
有一个问题就是，那chi square RP、RW 分别代表什么意思？然后怎么样叫好
？OK， 好，我们再看刚刚那个哈，那我顺便解释一下为什么要定那个值哈。OK， 好，来，这个 RP、RW 哈，这个我们叫做可靠度因子 reliable factor 哈。RP 简单来讲就是你的观察值减掉你的理论值嘛，对不对？把所有的这些值相减，也就是说每个角度的那个点啊，实验值跟理论值相减，全部把它加起来，除上全部的这个观察值这样子。那一般来说哈。这个我们会说这个值，我们是希望它小于6%，或者说你一般我们常讲科学希望小于5%的误差啦。其实这个就是我们一般在算那个误差值有没有我的标准值跟这个标准值与实验值相减这个比值啦。那6，因为我们这个抛的这个东西呢，它在统计上来说它的这个其实还有牵涉到一个数学，就是下面的 n 值是多少的问题。不过一般我们来讲，就是以6% 做一个标准啦。那 RWP 是在哪里？这是 W 它其实是一个导数，什么导数呢？你导射峰 peak 值的位置的导数。所以想想看，你越靠近导射峰，是不是这个越分母分之一？越靠近导射峰，讲那个差值越小，对不对？越小导数就变得越大，所以它在 peak 的地方会被加权很大。所以这个值是在 peak 处被加权的。那一般我们希望它小于10%啊，那其实小于9，其实是一个比较保守的说法。小于10%就是说，其实这也没有这么一定。老实讲，因为呢，这个东西又跟你的这个点数的多寡又有点关系。一般来说，我们做实验的时候呢，希望你的第一个intensity 希望大概在最好实验值是在5-6千点之下，然后点数呢，希望大概在这个 250点之内，一般 2θ 范围之内，一般是这样希望。这样子的话呢，你 Rp 跟 Rp 呢，小于6跟小于9呢，是我们一般比较在 publication 上比较认可的值啦。那 chi-square 呢 ？chi-square 其实有点像标准差啦，其实有点像 reduce 的 chi-square 有点像标准差，就是减缩 chi-square 我不知道怎么翻译哈，就是反正 reduce chi-square 会比较像标准差。那我们是希望它一般是希望它小于2，可是这个值呢，你注意到它 n 哦，所以我刚刚讲为什么 n 值希望小于250呢？因为你如果 n 值你想想看 n 值很大的时候，你发现你的chi-square就会小于1，0点多，有时候你开值这里头做的点数是好几千点的时候，你发现这个值会小于1哦。那有时候呢，你发现明明你犯的很好，可是你的开值怎么样都是很大，所以开值比较没有那么准，反而是这2个值是我们比较信任的指标。但是在那个 Toby， 其实这个值写 Jesus 那个人叫做这个 Toby，Toby 他有给出一个建议大概就是这个样子那当然有一些数学的理论，很多细节也没办法详细说但是他有写那个 menu， 如果你们有兴趣看那个 Jesus 2的 menu， 有写大概这个是他们的建议值。是这样，当然有他数学的理由啦，不是说随便我讲说6，你讲说3这样子。剩下一点点，好，我最后讲一点点东西啦就是说铝饭碗可以做什么事情呢我刚刚没有讲，本来讲说没有时间不够当然第一个你可以定结构的样貌这个就不说。第二个画电子密度图，这个我也不说了好，那第三个这个很常在研究上发现就是说这是一个，其实这是一个 perovskite 的样品啦那很多时候呢这个同学去做这个 perovskite 样品，它是一个掺杂的样品。那掺杂完之后呢，他去做实验的时候呢发现他多了一堆 pick， 然后就觉得这个样品做烂掉了，就把它丢了那我这里告诉你一件事情，是说其实有时候多一系列 pick 的时候，不是你样品做烂的，而是你做的结构，你做的更好了什么意思呢假设我的样品这个样品，这个 perovskite 样品，这个位置呢是蓝跟钡呢一半一半的交替，随机交替的取代，但是取代的比例是50% 的时候，它这个 phase 会叫做 PM-3M， 所以 pick 数会比较少。假设你的结晶非常好的时候，这个位置叫蓝，这个位置叫钡这个位置叫钡，这个位置叫蓝，是周期性的这样排列的时候，你会多一系列 pick 那很多同学会觉得说，做完了，老师我这个跟 paper 不一样，所以我做出来的是杂质，就把它丢了然后做了100次都丢了其实不对，其实它是做的非常好的，太好了，以至于多了一堆 pick， 所以有时候它不一定是杂质这是因为它结构的周期性变2倍了，所以多了一系列 pick 你看蓝跟钡随机交错，就是说假设我沿着这个周期性，我这样排蓝钡蓝钡蓝钡，就是随机但是比例一半一半的时候，这边的原子的散射长度是要算它们2个相加除以2。那要是蓝钡，那蓝跟蓝的 diffraction 跟钡跟钡的 diffraction 是不一样的，所以你就会多一系列 pick 这是一种情况可是有时候学生做了不敢给老师看，觉得他做烂掉了就把它丢了其实这个是不对的这是第一个。好，第二个呢，做这个实验也有一些限制你用 Xray 的限制就是你没有办法去分辨你的元素太靠近，因为 X 光是对你的电子数去做散射，所以呢，之前有个例子就是你看周期表是铁跟铜，对不对？它离得很近散射的强度是正比于散射长度的平方。所以比如说，假设你要从铜跟锌去分辨的话，2个几乎不可能铜跟锌一个是28，一个29嘛，2个平方差很少，所以分不出来所以有时候你同配会被 ref 力，有些 ref 力比较懂这个的话，你说我这铝饭这0.52、0.49他就跟你说抱歉，这分不出来那我们实际上依照这个结构，你看这个是 doping 嘛假设我这个铜跟铁互相交互 doping， 有这种 doping 形式，有这种 doping 形式，还有这种 doping 形式的话，我去做模拟给你看下面这张图是模拟图，把刚刚的4种结构全部模拟出来，你看得出不同处吗？ 全部长得一模一样，连强度的几乎都一模一样，所以你 Xray 没办法去分辨这种结构。这时候你就需要用别的工具，比如说像 Neutron 或者是别的东西去分辨。所以有时候你这种情况你没办法去跟人家讲说，你可以去分辨这些元素啊。那再来，当然这个是当时2个项的一个refine啦哈。这个同学他想要做这个材料，结果呢用这个材料去refine的时候，发现有系列并的对不到，然后呢想说它原料有什么呢？有氧化铁啊，去对，氧化铁可以对到一系列，所以最后可以怎么样？我又把2个放进去，全部都可以refine到了，而且我告诉他说，它氧化铁多放了多少。新版的巨石，旧版的巨石你要自己去算，它的比例呢是一个 unicell 的比例，看一个 unicell 里头有多少的化合物的这个 z 值是不一样的啊。那新版的它直接告诉你说，你的样品里头，比如说铁有多少克，这有多少克，你到时候做样品的时候你就少放，你就可以得出纯项了，这个可以做这件事情啊。然后呢，prefer orientation 有些 prefer orientation， 比如说像锡锡很软，对不对？这个是同一个样品你只是把它压下去而已同一个样品同一个样品同时间做，它一开始粉铺得很松，做起来长这样子，结果一加压，200 pik 就被压下去了。所以有些材料你压粉的时候，你们在做铺粉，一般1号材料它叫压粉嘛，对不对？有些粉你要很小心软的样品你去压的时候会这样子然后你refine到时都refine不出来，明明就同一个样品你只是加压一下而已而且是粉是轻轻的压，还不是很大力的压还有什么呢？我来往下好，晶格常数会随着尺寸去变那这是另一个例子啦然后变温它也会热胀冷缩这个大家应该都知道了然后它可以算这个键长键角的变化，可以跟拉曼去做对照所以这个红色的图呢是某个键长比如氧化锰的键长，或是 TBO 的键长跟拉曼膜的这个对应然后粒径，对我刚刚不是讲，刚刚魏教授问说有没有筛粉，有没有那这个是反过来，反而是有没有风型，有没有去换算它粒径的分布大概长什么样子那用 SEM 做出来是这样子的话，那 Xray 也可以去做然后呢，我们也可以去算它的应力那现在因为巨石度都内建的啦所以这应力，这是我以前写的程式啦不过现在应该看人也可以用啦，也可以不用啦就可以去算粒径跟应力了好，那其实有一个很常用的一个技巧叫做算它的价数本来如果你们有那个带 notebook 带你们算的话这是一个氧化铝的例子啦这是 bond valence 上的 parameter 这个表在这边如果你去算结构计算完后，它会帮你键长跟键角。你有键长呢，你就可以去算用 bond valence parameter 去算你的价数是多少。所以有时候你原子放在什么位置的时候，你可以去算出它的价数是多少。那其实像刚刚前面讲的 charge ordering 在室温下的时候，你会发现有些原子位置它就是3.5价，但是到低温的时候就是3价、4价会在特别位置出现，你就可以算出这个用bond valence算出哪里是3价原子，哪里是4价原子。有时候可以这样去做这件事情好，那最后应该是这个啦这个当然是比较更特别一点啦我可以由键长去算 low spin、high spin 跟它的 spin value， 然后呢去估计我如果去做 screed 的话，距离长是多少？你要多少量 screed 才量得出来就是说你有键长对不对？那这就有告诉你说你在什么样的周围，比如像这周围有6个键结的情况下呢，它应该要有的原子这个半径是多少那比如说假设这是氧化锰，我去refine出来它是1.93那6轴坐标里头呢，氧的大小是1.4，那我扣掉之后，我就知道锰的这个离子半径应该是0.53。那0.53在这个6价结构下是锰4，那 spin state 长这样子。那这 spin state 呢，假设我在高温的情况下，我就可以用这个公式去算。假设它没有一些晶体场的问题的话，我可以得出它可能的距离常数值大概是1.87 EMU/K。那一般的 screed 大概10的负5次，绝对值10的负5次到 EMU， 你就知道准备多少颗氧你去做谁就可以了。 所以这是另外一个比较奇怪的，请说。
我最后问一个就是说那个 Z 值，可以帮同学讲一下这个 Z 值是什么，然后它对于 Neutron 跟 Xray 的重要性。
OK， 好，我刚刚提到一个 Z 值，我没有解释是什么哈。一个 unit cell 里头，比如说我们今天讲 NaCl 呢，你想想 NaCl 在化学式只有一个 Na 一个 Cl， 对不对？可是在一个 NaCl 它是一个 FCC 结构 ，FCC 结构里头 Na 跟 Cl 呢，其实各要放4个，才能够把这个 unit cell 给填满。所以呢，这个 NaCl 我们会说它的 Z 值叫做4倍的化学式，4倍的化学式。那这个重要性在什么地方呢？因为 Xray diffraction 或 Neutron diffraction 或是电子的 diffraction， 它的强度比是正比 unit cell 的。所以有时候我们去做 refine， 刚刚前面在做 refine 的时候，不是有那个 phase 的比例吗？其实它是 unit cell 的比，可是呢，你用 NaCl， 假设我 NaCl 去跟另外一个材料，比如说Vanadium 钒金属它是这个 PM-3， 它一个 unit cell 只有2颗，它的 Z 是2。那你去做这个 Xray diffraction 的时候呢，假设你得到这个材料里头钒跟 NaCl 的强度比是1:1的话，事实上它的化合物就是一个化学式的比例会是多少呢？会是2:4。会是2:4，所以 Z 值代表是一个 unit cell 里头有多少个化学式单位的东西在里面。然后呢，这个 Z 值呢会反映出你一个 unit cell 要被加权多少倍才会等于你的那个单一化合物的贡献，大概意思是这个样子。所以不管在 Neutron 在 Xray 全部都是一样的。所以你有时候看到 paper 会跟你讲这个 unit cell 里头的 Z 值是什么 ，Z 值是多少，代表是它是几倍的这个单位化合物的这个数量这样子。好，我看时间也差不多了总算把这个2小时撑过了
好，那我们谢谢杨老师，谢谢。
好，谢谢大家，谢谢。
这个播音。不好意思。我们6点半才用场，所以请大家可以趁这个时间先去 check in。如果是住这边的，那如果不是住这边的贵宾，就麻烦先在这边休息一下。我们6点半在1楼，就这个正楼下用场。麻烦提领行李，直接跟柜台拿你们的钥匙。
那你住这边吗？还是那边？那我们只能在这边等。不是呀，他也是在我们这边。对啊，那可能就所以你是要在这边起。